Hi, good afternoon, everyone. My name is Ramadi Trimananda, and today I'm going to present our work, packet-level signatures for smart home devices. This is a joint work between myself, Yanis Barmakan, Athena Markopoulou, and Brian Dembski, all from UC Irvine. So let's imagine that we lived in this beautiful home, and then we decided to add smart devices, plugs, light bulbs, thermostats, and even security-related devices such as cameras, and doorbells. And one nice evening, we gathered with our family upstairs, and then suddenly we realized, oh, I forgot to turn on the security camera at the front door. So we just take our phone, and then we control the front door camera. So when the phone communicates with the device, they generate some LAN traffic. Subsequently, when the device talks with the cloud, for example, for some status updates, they generate some WAN traffic as well. Similarly, when the phone and the cloud communicates, because the phone is running the vendor's app, they generate some WAN traffic as well. So we can see here 3 communications are going on through our smart home router. And even though a lot of these devices have encrypted their network communication, for example, via the TLS protocol, an adversary can still look into the traffic metadata, such as packet lengths, directions, orders, timing, and so on and so forth. So this work explores how such an adversary can analyze the traffic metadata to infer what we're doing with our smart home devices. We investigate 2 kinds of adversaries. The first one, a WAN Sniffer. A WAN Sniffer observes the traffic in between the WAN interface of the home router and the vendor's cloud, for example, the ISP. This adversary looks into the device cloud and phone cloud communications. And this adversary can look into the TCP/IP packet. They can see the IP addresses of the endpoints, but they cannot see the MAC address of the device. The second one, a Wi-Fi sniffer. A Wi-Fi sniffer sits in close proximity to the home router. They can turn on the monitor mode on their laptop, and they can see the radio packets going in the 3 communications. This adversary cannot look into the TCP/IP packet because it's encrypted. They cannot see the IP addresses of the endpoints, but they can see the MAC address of the device. The state-of-the-art of IT traffic analysis, the research community has looked into the traffic from specific protocols, such as Zigbee and Z-Wave. Some researchers have looked into volume-based signatures, meaning that when there's a volume spike, there's an event. Some other researchers have also looked into machine learning approaches, and they use network statistics as features. The main limitation of these approaches is that we have to collect enough traffic in order to perform the statistical analysis, whereas IoT devices tend to be simpler, and they tend to generate less traffic. So the question becomes, can we actually perform such an analysis using limited amount of traffic? Some other researchers have also collected IoT datasets, and they perform wide-scale device study. They study the network traffic characteristics, such as device protocols and so on and so forth. They released a few public datasets, such as the Monitor and YourThings datasets that we use in our evaluation. And so I presented to you the background and the problem statement of this work. Let's switch gears a bit and look into the key observation that we made in our work, packet-level signatures. So going back to this smart home diagram, we see the 3 communications going on through our home router. Now we observe in more detail that whenever we control a device, for example, we turn on the plug, our phone always sends a request to the plug, and the plug responds with a reply back to the phone. So a ping and then a pong. And similarly, in the device cloud communication, when the plug sends some status updates to the cloud in the WAN traffic, we can also observe this request-reply pair due to the network communication protocol. Similarly, in the phone cloud communication, whether the phone is connected locally or remotely. For example, we sit at a Starbucks, and then we want to turn on the smart plug at home. Now, in this communication, we can also observe this request-reply pair. And similarly, when the cloud relays the command to the plug, we can also observe one more time this request-reply pair. Now, a similar situation, we also observed this request-reply pair when we use home automation service. For example, we set up a rule at 5 p.m., turn on the plug. So at 5 p.m., the home automation service is going to make a request to the vendor's cloud. And when the cloud relays this command to the plug, again, we see this request-reply pair. So we made a more detailed observation. This is the simplest case, the TP-Link plug. Not only that we have found such a pair of request-reply packets, but also we have found that this pair comes with deterministic and unique packet lengths and directions. So here, for the TP-Link plug, every time we turn on the plug sends a packet with length 556 bytes to the cloud. And the cloud responds with a packet with length 1293 bytes. And this is deterministic, meaning that we can see this pair. It appears once per on event. I'm introducing this notation that I'm going to use in this presentation from this point onward. C556 means a packet from client to server, from the plug to the cloud, with length 556 bytes. And S1293 means a packet from a server to client, from the cloud back to the device, with length 1293 bytes. And this is in the device-cloud communication. A similar situation for the off event, although this time there's a 1 byte difference in the request-reply packet pair. And we can see here that the packet pair is unique. Each packet pair is unique for each event type. Similarly, we observe a similar deterministic packet pair for the D-Link plug, although this time it appears in the phone cloud communication. And once again, for the SmartThings plug, we observed a similar request-reply pattern, but this time the pattern is more complex. And this appears in the phone cloud communication. We can see here 2 TCP connections going on between the phone and the cloud. The first one on top, the phone and host number 1, the first TCP connection contains one sequence of packets that consists of one pair of request-reply packets. At the bottom, we can see a TCP connection, the second TCP connection between the phone and host 2. And it consists of a sequence of packets that contains 2 pairs of request and reply packets. So this far, we have observed packet level signature of an event, which is one or more sequences of packets. And in each sequence, we can find one or more request-reply packet pairs with unique and deterministic packet lengths and directions. So based on these initial observations, we formulated 3 research questions. The first one, how can we automatically extract packet level signatures? We're curious to find out whether such signatures also exist in other devices. And such an automated tool will enable us to answer the second and the third questions. How universal and how unique these packet level signatures are. So let's answer the first one. I present to you the Ping-Pong system. In an automated extraction system, we want the system to extract these pairs and to form longest possible sequences to make the signature as unique as possible, and then we can use the sequences as a signature. For Ping-Pong to extract a signature for an event, we have to train it. So for this, we need the device, and we need to generate a number of events as training samples. And since we extract the signature from packet pairs, first we have to perform data collection to get a network trace for the device. And at the end of the data collection process, we will have a trace that contains the traffic from the generated events. But in this trace, we can also find traffic that's not related to the event. So we need to perform trace filtering. And in this trace filtering, we will get a subtrace that contains only the traffic from, that's related to the event. However, this subtrace contains a mixture of different TCP connections, as the device may communicate with different endpoints in the cloud. So we have to reassemble individual TCP connections, and then we form packet pairs in the individual connections. And now we have to select the pairs that are related to the event. And to do this, we have to perform pair clustering, because sometimes the packets can come with a slight variation in the packet lengths. So we perform pair clustering to group the pairs into different clusters. Each cluster contains packet pairs with similar lengths and same directions. And then we have to select the clusters whose number of packet pairs is equal to the number of generated events, because we made an observation that a packet pair that's related to the event actually appears exactly once per event. And then we perform signature creation. We form longest possible sequences from the selected pairs, which becomes our candidate signature. And upon validating that candidate signature, we finally get a signature for an event. And this is the simplest example of such a signature. This is the on-event signature for the TP-Link plug. A more complex example here for the Arlo camera. It's an on-event as well. There is a signature with two sequences. The top one, a sequence of two pairs, and the bottom one in blue, it's a sequence of one pair. And some of the packets in the sequences, they have a range of packet lengths. I encourage all of you to check out the paper for more detail on the training and also on ping-pong detection. Now, I've answered the first question. Let's now answer the second and the third questions. How universal are these signatures? We extracted signatures using ping-pong in 3 communications: phone device, a device cloud, and a phone cloud. And we also performed the experiments for 2 adversaries, WAN and Wi-Fi sniffers. And we tried different ways of triggering the phone. The first one, local phone, we extracted signatures for 18 devices in our corpus. This is the result for the plugs. And we can see that for every device and for every event type, there's a unique signature. And we got really high recall rate for both WAN and Wi-Fi sniffers. Similarly, for the light bulbs, the thermostats, sprinklers, and home security devices. We performed similar experiments on a public dataset monitor from Northeastern University. We extracted signatures for 21 devices that don't exist in our corpus, including more complex devices such as voice command devices, smart TVs, and even a fridge. We also performed comparison for 5 common devices, and we found that the signatures are either exactly the same or really similar. And now we also tested remote phone and home automation triggers. And we also extracted signatures from our devices. And this time, the signatures actually appear in the device cloud communication because the phone was connected to a remote network. And all these, we perform matching with average recall of over 97% for both WAN and Wi-Fi sniffers. Now, in terms of uniqueness, our signatures can distinguish device type, event type, binary and non-binary, such as intensity and colors for light bulbs. And even for same vendor devices, we experimented with ping-pong on 6 TP-Link devices, and we found that the signatures are distinct with respect to device model and also event type. And even for devices with similar functionality, such as a plug and then also a power strip. We also performed negative control experiment on 3 public data sets. We tested our signatures using ping-pong. We performed ping-pong matching to detect the occurrences of our signatures in the traces that don't have devices in common with our devices. We used Your Things, UNSW, and UNB datasets with over 440 million packets. And we have found that the false positive rate is, in average, 1 false positive per signature for 40 million packets. So in summary, I presented to you packet-level signatures. They can distinguish event types with minimal set of traffic features, only packet lengths and directions. And they apply to 2 adversaries, WAN and Wi-Fi sniffers. And they're applicable to many devices as well. In our paper, we have a lengthy discussion about possible defenses. And they are resilient to traffic shaping and VPN encryption because they don't hide the packet lengths and directions, but they can potentially be defended against by packet padding. In a more positive way, we can use these signatures for profiling and network monitoring. Some limitations: for Ping-Pong to extract a signature, we need the device to train. And the signatures may also vary over time, just for some devices. For example, when there's a firmware update. And so we have to perform retraining with the device. And the signatures apply to 95% of devices, with exceptions. For now, Ping-Pong does not support UDP-based devices, but they are straightforward to be supported. And there are also some devices which repetitive pairs for an event. So to conclude, I've presented to you packet-level signatures for smart home devices, which are based on request-reply pattern. And they use only 2 features, packet lengths and directions. And I've shown to you the automation using Ping-Pong that can perform extraction and detection. And I've shown that the signatures are universal and unique. Thank you very much for listening to my talk. Please check out our paper and also software and datasets release. Thank you very much.
Hi, Murat Kantarcıoğlu, University of Texas at Dallas. My question is that when you try on new data set, you have to retrain and create new signatures for the new devices, right? You can't just apply for the signatures you have on totally unseen device. So you have to see the device before.
So we have two different features for Ping-Pong, extraction and detection. So for the new data set, the monitor data set, we performed extraction for 21 devices. So those are new devices. Thank you for your question.
Saurabh Bakshi from Purdue. So you showed that there are unique packet-level signatures for each device. So how easy or how difficult do you think it would be for each device to not just pad, as you pointed out, but even randomize how many bytes it pads for each request? And then the end device can just discard the padded bytes.
You mean how easy to pad the bytes for each device?
And randomize how many bytes you're padding, either by the device itself or by some intermediate between the 2 devices.
So thank you for your question. I think what we have looked into, the easiest way to pad the bytes is by padding the packet length into the same length for every packet. And then we looked into TLS padding, for example, and also VPN-based padding. But padding in itself, do I answer your question, by the way, so far? OK. So padding in itself, we see that it's not that effective because we can still see that the packet is going from the device to the cloud. And for example, the simplest case, the TP-Link plug, we can actually see that the pair actually appears as a TLS application data. So even if we pad the packet length into the same length, right, we can still see, oh, this packet actually is an application data. It's still a signature. And so what we can see is that this packet padding can be a part of a bigger toolbox that we can use together with a VPN, for example. So we can implement VPN with packet padding so that everything is going to be lumped into one connection. And so we cannot differentiate whether this is application data or TLS or different protocols.
One more question. So how frequently do these signatures change? I mean, are they transient? Has something changed while you were doing this paper? Or?
Yes, so to answer that, I actually put something there. Signatures that vary in certain packets. So for the TP-Link plug, we collected the signatures like 3 times. So the signature with 1 pair They appeared back in 2018. And then recently we recollected or we extracted the signature for 2019. And then we saw two different signatures. So depending on the device, right? We also observed devices that don't change over time. Yeah.
Thanks for an interesting talk. This is Hao Ting from the University of Nevada. So my question is, so you generate this unique signature. So if there is an attacker, how difficult that will be if they use some specific circuit to reproduce this signature, and how cost that will be if it's possible? Thank you.
Thank you for the question. So as an attacker, I think what we can do is we buy, for example, we want to attack a TP-Link plug. We just buy maybe one plug first, and then we extract the signature using Ping-Pong for that plug. And then if we're curious to know whether there is variability in the packet lengths, then we can, for example, buy more plugs, the same model, and then we see the variation in there. We have something in Ping-Pong, you can check out the paper. We have something that's called relaxed matching. So for example, for the TP-Link plug, there's a signature that consists of 5 packets, but only 2 of them have slight variation, but very, very minor variation. So we can use that relaxed matching to actually detect the presence of that signature in a trace.
Does the relaxed matching reduce your accuracy?
It might reduce the accuracy in the sense that we might no longer be able to differentiate on from off, but then we can still see that signature in the trace.
Right, do we have any more questions? If we don't have questions, we'll conclude the session. Let's thank Ramadi and let's thank all the speakers. And thank you again for coming.